Thanks, Ron. So I think there was a couple of questions on what is RAG earlier. And in this talk, I'm going to kind of explain some of those concepts of what RAG is and vector databases are, and try and explain them in a way that people can relate to in, with clear mental models and metaphors. Okay. So a quick intro to Trellix. Trellix is a pure play cybersecurity software provider, right? We provide security to over 40,000 customers, and that includes over 80% of Fortune 100 companies. Okay.
Alan,
we protect some of the.
Alan, can you maybe just adjust your mic? Sometimes it's a little hard to hear you.
Okay. Is that any better?
A little bit, yes. Okay.
Okay. So we're doing a lot of work with AI at the moment, right? So AI is, I guess, a double-edged sword in security, right? Bad actors are using AI, and I suppose generative AI has lowered the barrier of entry into AI generally, right? Because now all of a sudden the P part of GPT is pre-trained. So all of a sudden you've got pre-trained models that are available to everybody to use, really, right? So Trellix, we aim to provide a counterbalance to that dynamic, right? And protect our customers with the bleeding edge of AI. Okay. So our Trellix Wise is our AI offering, and that gives bleeding edge AI capabilities to our security stack. Okay. So some of the functionality we give to our customers are, we do natural language queries into their security data, so they can write queries in plain English. We do AI assisted triage and investigation. We roll up complex detections, right? Very complex detections with deep security domain knowledge, and we roll that up into accessible, human readable English, plain English, right? We use AI to risk score. We do AI driven threat hunting and investigations, proactive investigations with AI. And we also use vector search to do RAG and RAFT. Okay, and that's what we're going to look at a lot more closely in part of this talk. Okay, we also do fine tuning. We train our own models. We're looking at working with security small language models as well.
Alan, now we can hear you. Is it just me? Are other people not hearing Alan? All right, just sit tight for a second.
Oh, can you hear me?
Yeah, can you speak a little louder, Alan?
Okay, can you hear me? I'm just moving over to my my open mic here.
Yeah, I think, yeah. You might want to, just so we don't have just your eyeglasses in the camera, why don't you turn off the video and speak closer to the microphone? That way we know you're presenting live and can hear you a little better.
Sure, just bear with me a second. Okay, so let's keep going. So what is RAG, right? If you're building security applications, you are going to end up doing RAG. Okay, if you're building any AI applications, right, you're going to want to get your data or your customer data into a model and do an inference over that data, right? And that's where RAG comes in, right? So if we break down the acronym RAG, right, it's useful to break that acronym down. Okay, RAG stands for Retrieval-Augmented Generation. Okay, so retrieval means that we retrieve data from a data store. Augmented means that we augment the prompt that we send into the AI. And generation means that we use that data to generate a response, right? A useful response to a customer or to a user. Okay, so a good analogy for non-RAG, right? And RAG is a closed book exam versus an open book exam, okay? A closed book exam, right? When you go into a closed book exam, you rely only on the knowledge in your head, right? To answer a question, okay? And that's what a non-RAG inference is like, okay? You might ask the model, tell me about who won the football, or, tell me about some security techniques, okay? And the model, if the model knows that and was trained on that data, it'll tell you about the security techniques, right? RAG on the other hand, can be thought of in the sense of an open book exam, okay? So with an open book exam, you have access to relevant data, okay? And you can use that data to back up your answer and give credibility and relevant citations for your answer, okay? So crucially, RAG also solves the knowledge cutoff problem, right? So in AI, you have a knowledge cutoff problem with generative AI in the sense that when a model was trained, the model only has knowledge up and as of the time that it was trained, okay? So for example, with ChatGPT 3.5, knowledge cutoff time is January 2022, okay? So with RAG, you can augment the knowledge that's built into the model by pulling your domain adapted data relating to your business into the model and get the model to provide inferences on top of your data, okay? RAG is also crucial for explainable AI, okay? And responsible AI, a couple of the other speakers touched on responsible AI, right? That's critical if you're doing anything with AI. Providing responsible and explainable AI is really important, right? So if you give an answer in an exam, or if you write a paper, or anything like that, you will get credibility if you give citations and references to back up your answer, okay? When we give an evidence-based answer, that answer is much more credible and it's much more grounded, okay? So RAG will help to ground the AI answer, right? And it will give much more confidence and avoid hallucinations in AI answers, right? So strictly speaking, RAG can work with any data store, okay? It doesn't have to be an AI-capable data store, okay? But increasingly, vector search is one of the first things we think about when we talk about RAG, okay? So a vector database is an AI-capable database, okay? That is, I guess, it provides a semantic search, okay? So we're used to doing database searches using SQL and keyword types of searches, right? A starts with type of a search is this keyword in the data, okay? Whereas vector search operates at a higher level, on a semantic level, where we compare things semantically, okay? A great analogy for vector space and a vector search is actually a supermarket, okay? So everybody here is used to going into the supermarket, into the store to buy their food, okay? And if you went into the supermarket, you would have a reasonable expectation that apples would be in close proximity to oranges. Why? Because apples are semantically similar to oranges, okay? You would not expect oranges to be in proximity to, say, shampoo, because shampoo is not semantically similar to an orange, right? And a vector database works very much the same way, right? So it takes your data and it maps it out in vector space, and things that are semantically similar are in closer proximity to each other in vector space, okay? So when we compare the distance between an apple and an orange, that is basically a distance metric that we're applying on the database, okay? So another example of a vector space, right, that most people on this call are probably quite familiar with would be the Gartner Magic Quadrant, okay? So the Gartner Magic Quadrant is a vector space of just 2 dimensions, right? When we talk about vector databases, we are talking about hundreds or thousands of dimensions, but it effectively works the same way, okay? So if we were to look at, say, for example, if we were to look at, say, AWS, and we wanted to see what were the 2 cloud providers that are closest to AWS, we would do a k equal to 2. We do a KNN, a k nearest neighbor search. If we set k to be 2, we would get Microsoft and Google, and vice versa. If we did the same search for Google or Microsoft, we'd get the same answer, right? However, if we were looking at Huawei Cloud and we set k equal to 3, we would expect to get Tencent Cloud, Alibaba Cloud, and IBM, okay? So that basically is, you know, an example of vector space and doing a vector search, okay? So if something's semantically similar, we can look for things that are similar to the things we're interested in, right? And this can become extremely powerful, okay? Right? And it can be very powerful, especially for security data, right? So our customers, you know, part of what they do is threat hunting, okay? They may, for example, see, you know, get a detection from one of our systems, and then they might want to do a deeper dive investigation into the cause of that detection or that alert, okay? So an example would be, let's say, you know, what we're doing is we're capturing trace information, event information from all of our customers' devices, laptops, phones, all their endpoint devices, okay? All the activity that happens on their devices. And, you know, sometimes what happens is after an alert happens, our customers want to probe that data and ask deep questions of that data, right? This is an example of what that data might look like, okay? In this is I suppose, a table showing a database that has command line activity that you might see on a typical Windows laptop, okay? So you can see kind of a lot of banal commands here, service host.exe, notepad, and so on and so forth, right? So there's one malicious command in here, right? One command of huge concern, which is a PowerShell command, right? This PowerShell command has a lot of red flags, right? That our security software would pick up on very quickly, okay? So the one big giveaway that's there straight away is that it's using this -enc flag, and it's passing in base64 encoded commands into the PowerShell, right? That's a typical tactic to obfuscate and to hide the true intent of what's happening in the script, okay? There's a couple of other red flags like the -no-op, -sta, -w1. What they do is they suppress confirmations and they suppress errors, okay? So this command is trying to fly under the radar, okay? So what we can do is we can load this data into a vector database. We can use our Trellix Wise AI functionality to ask questions of that data in plain English, right? We can literally ask questions. We can type out questions in plain English, like, are there any PowerShell commands using obfuscation, okay? What our AI can do then is it can give you, you know, a breakdown, a complex threat or a complex detection, and explain that in security domain language and secure in terms, you know, give a plain English explanation for precisely what is happening to the user, okay? So an example here would be that our AI has de-obfuscated the obfuscated base64 encoded command line. It's given a clear text output for the command line, right? And it's telling us what's happening under the covers of that obfuscation. So the AI then breaks down and explains to the user the step-by-step what the malicious malware basically is trying to do, okay? So it tells us that it's disabling prompting, confirmation techniques, that the script is encoded to avoid inspection, and it actually goes further. It explains what's happening within the obfuscated text, okay? So there's a lot of very concerning things happening here, right? What's happening is that there's this IFEO option, which is a classic thing that malware tries to do, that more or less is trying to kind of attach a debugger into a space, right? Into a process, so that it can maliciously interact with the process, right? And then our AI explains exactly what is happening and tells the user that, you know, that command should be blocked and investigated immediately, and, you know, it'll also give potential follow-up actions to happen, right? So let's go back to vector search and explain some of the nuances of vector search, right? And RAG, right? So there's two things going on when you do a vector search, right, that you need to think about, right? So there's a distance metric and there's a search algorithm, okay? So the distance metric is basically how you compare two different vectors, okay, within to assess your similarity, right? And there's subtlety in those distance metrics, right? The three different most common metrics you'll come across are Euclidean distance, cosine similarity, and dot product, okay? They have some nuance between them, right? Euclidean distance is, I guess you can say, comparing two things as the crow flies, okay? How close are they to each other, right? In the supermarket metaphor we had earlier, Euclidean distance would be simply how far were the apples away from the oranges, okay? The dot product and the cosine similarity will give a more kind of a nuanced type of a similarity, a thematic similarity, okay? So dot product, for example, will say how directionally aligned the two vectors are, right? So, you know, if you went into that supermarket and you wanted to get, say, a bottle of Merlot, okay, and you didn't know where the Merlot was, the bottles of Merlot where the wine was, you may spot the beer at the end of an aisle, and you know Merlot is directionally similar to the case of beer, so you walk in the direction and you get your bottle of wine, okay? You could also use a search algorithm, okay? We talked about KNN, okay? KNN, we give an example of KNN, which is K nearest neighbor, right? So KNN will be like, you know, if I'm looking for an apple, would be like walking through the supermarket and asking the question of every single product in the supermarket, is this an apple? Yes, no. Is this an apple? Yes, no, okay? That will be highly accurate, but it will be highly inefficient, okay? So why? Because it's an ON problem, right? The more items that are in the supermarket, the more comparisons you need to do, okay? So that obviously won't scale if you have a retailer, the scale of, say, Amazon retail. Obviously, comparing every single product in Amazon retail would be incredibly inefficient, right? So that's where ANN comes in, which is approximate nearest neighbor. An approximate nearest neighbor is a basically trades off a little bit of accuracy for a dramatic improvement in performance, okay? And these are the kind of things we look at to kind of scale our AI to give, you know, a quality user experience to our customers, okay? So let's break down ANN a little bit more, right? The two most common approximate nearest neighbor indexes you'll come across when you look at a vector database, right, will be LSH and HNSW, okay? LSH is location sensitive hashing, right? And if we go back to our supermarket analogy and just labor that metaphor a little bit more, LSH would be like dividing the supermarket up into aisles, okay, right? So, you know, we expect certain things to be in certain aisles, related things to be in certain aisles. And, you know, if I'm looking for an apple, I don't need to walk all over the supermarket. I can go straight to the fruit and veg aisle, and I'll, you know, find my apple in the fruit and veg aisle, right? And I can do that efficiently. HNSW, we'll take a look at that just next. So the TREDX use case, actually, we are very focused on accuracy, right? So we do a flat index, a KNN index, okay? And we kind of use our heuristics to downsample and, you know, get down to a pretty good downsample, and we do we throw compute at it and we do a KNN inference, KNN search across the vectors, okay? Let's have a look at HNSW, okay? Because this is interesting. So HNSW is actually the most common, probably the most efficient index that you will get when you do vector search, okay? HNSW stands for hierarchical navigable small worlds, okay? And this is often the default index you will have set on a vector database. I'm pretty sure it's the default index on Weaviate and ChromaDB. And this is often the one that you will get out of the box, right? Why? Because it gives you very high accuracy, minimal trade-off in accuracy for a very high improvement in performance. So how does it work, right? When you look at this diagram here, that's quite complex, okay? It's probably a little bit difficult to relate to straight away, okay? But if we have a useful metaphor, okay, and a useful mental model, this actually becomes very simple, okay? So the HNSW index is a graph, okay? And we can think of HNSW index and we can compare it to the public transport system, okay? If I wanted to get from London to Bondi Beach in Sydney, Australia, okay, and I wanted to do so over public transport, I would use multiple modes of public transport, okay? I could travel over land, okay? A friend of mine did that out of a sense of adventure, but it would be a very highly inefficient way to do it, okay? The efficient way to get from London to Bondi Beach would be first to get on flight, okay, and fly from London Heathrow to Sydney, right, over the aviation network, right? So what are we doing there? You're taking a very large hop from London to Sydney, and you're using a sparse network to travel a vast distance very efficiently, right? Then what you do is you drop down to a less sparse network, okay? So I might drop down to the train network, for example, and in a few hops, I will get from the Sydney airport, probably to Bondi Junction, which is a train station near Bondi Beach, okay? And then what I would likely do is I will get on the bus, and what I'm doing there is I'm going out to a dense network, right? Making, a dense network, taking hops over a shorter distance, getting me exactly to where I want to be, right? That's how a HNSW index works, okay? Right? So let's wrap up. And if you're doing RAG, okay, and if you are thinking about building an AI application, right? If you're building AI applications, you're going to be looking at RAG very quickly, right? Because you need to get your business domain data into the AI, okay, right? And inherently, when you're doing that, you're going to be looking at RAG, okay? The model can't connect to any data itself. What's happening when people talk about AI connecting to data, right? What they're really saying is that the AI application mediates between the model and your data, right? And that's what RAG is, okay? So putting it all together, right? We need to select an embeddings model, right? There's lots of embeddings models out in the market. There's kind of commercial models, open source models, okay? The main criteria that you look at when you're selecting a model is the dimensionality of the model, okay? When we looked earlier at the Gartner Magic Quadrant, we said that was basically a vector space of 2 dimensions, okay? But in general, the more dimensions you have in your vector model, your embeddings model, the more rich knowledge you have and the more semantic knowledge you have compressed into your data, okay? The first thing you look at there when you're selecting your model would be the MTEB leaderboard, okay? Right, so you combine looking at dimensionality and the MTEB leaderboard to find the good players there, right? Popular models there would be Cohere. You can use Mistral for generating embeddings as well. There's fine-tuned versions of Mistral, and of course OpenAI is a leader there as well, right? One thing to be aware of, generating embeddings is slow and it's computationally expensive, right? It's computationally expensive both in terms of wall time and also in terms of cost, okay? So you need to be very efficient at doing that. There are ways to scale that. If you want to scale that, one of the ways to scale that would be, you can use technology like SageMaker from AWS, and Ray.io is an open source framework that will help you scale generating embeddings, okay? We already spoke about vector indexes and distance metrics. So tuning of your vector index and distance metrics is critical. One thing I would say if you're looking at building an AI application off of a vector database would be to start with KNN first. We talked about KNN and ANN, okay? So KNN is 100% accuracy. Use that as your baseline. Then look at the ANN algorithms and compare your loss of accuracy against the KNN, okay? The flat index as your benchmark. Hybrid search is where you combine vector search with keyword search, okay? So vector search can be tricky to get right? But you can sometimes get spurious results. But combining that with most vector databases now support a hybrid search where you can weight the search towards a keyword search, and that helps keep the vector search grounded so you don't get too many surprising results, right? And finally, a re-ranking model is, one of the things that's emerging a lot is applying what's called a re-ranking model on top of your vector search results to downsample, and further refine to get better and more relevant results out of your vector database. An example of a re-ranking model would be from Cohere. There's various other re-ranking models available on Hugging Face, and so on. And that is it from me, Ron. I think you're saying that I'm pretty much out of time. So back to you, Ron, and thank you if anybody has any further questions and wants to talk about vector databases. Very happy to oblige. Thank you very much.